Hi everyone, this is Yiming. I'm a PhD student from the Hong Kong University of Science and Technology. It's my pleasure here to introduce our work, Zebra when temporal graph neural networks meet temporal personalized PageRank. Here is outline and I will start from the background and motivation. Graphs are everywhere and serve as the foundation of many real-world applications like social network, citation network, and knowledge graphs. Recently, graph neural networks have achieved huge success in those graph-based applications. The main idea of GNN is to recursive sample and aggregate neighborhood features to generate node embeddings. The key issue here is that many real-world graphs are dynamic. The social network like Twitter is a good illustration. When a person joins a platform, a new node is created. When they follow another person, the follow agent is created. When they change their profile, the node is updated. Such dynamic graphs support a wide range of applications like link prediction and fraud detection. The challenge here is that static GNNs fail to learn a good representation of dynamic graph because they can now capture how the graph evolved. Ideally, we help the model support the change of graph structure and can make predictions at any time point. For example, we can predict the representation of a node in the future. To this end, temporal graph neural networks are developed to learn temporal embeddings on continuous time dynamic graphs, which are represented as a sequence of timed interaction. For example, in the dynamic graph, the dotted line with time step T6 represent an edge of neural interaction, while the solid lines with time step indicate historical interactions. So let the node time pair V1 T6 be node V1 and time step T6. To compute the temporal embedding of V1 T6, a two-layer TGN recursive sample the temporal neighbors of V1 T6 and it aggregates the corresponding neighborhood features. Specifically, V2 T5 is the temporal neighbor of V1 T6, and V1 T4 is a temporal neighbor of V2 T5. The temporal sampling proceeds in inverse chronological order, and we do this kind of temporal sampling layer by layer. Besides, for each layer, TGN employs an attention module to learn the weights of neighbor nodes. In summary, TGN identify influential neighbor nodes with the tedious recursive temporal neighborhood aggregation. In this paper, we study this question. Do there exist influential nodes that we can utilize to accelerate the computation of TGNs without compromising model accuracy? If so, we can reduce the computational cost of TGN by directly searching and aggregating the most influential neighbor nodes. Next, I will introduce our framework. We start by investigating the relationship between temporal massive passing in TGN and temporal random walks on dynamic graphs. For TGN, the one help neighbor weights W1, W2, and W3 used for feature aggregation sum to 1. On the other hand, the one-step temporal random walk probabilities P1, P2, and P3 also sum to 1. Our key observation is that one help neighbor weights learned by TGN implicitly defines the one-step temporal random walk probabilities on dynamic graphs. Based on this observation, we analyze how each input feature of TGN affects the final learned temporal embedding. Specifically, we measure the influence of an input feature X on model output Y by the magnitude of the corresponding partial derivative. Then we build the theoretical connection between TGN and temporal random walk on dynamic graphs. Our series shows that the normalized influence score of V1 T4 with respect to V1 T6 is proportional to the probability that a two-step temporal random walk starting from V1 T6 stops at V1 T4. We then get some implication from the theoretical analysis. So it's possible to identify influential neighbors if there exists a method that is able to sufficiently capture the diffusion process on dynamic graphs. In this way, we can prune insignificant neighbors and avoid the laborious process of recursive temporal message passing. The challenge here is that as we can now know the neighbor weights in advance without actually running the TGN model, how to estimate the corresponding temporal random walk probabilities? To solve this challenge, we get key insight from the behavior of vanilla TGN. The figure on the left shows the impact of stray neighbor samplers on the performance of a two-layer vanilla TGN. So given a target node, the weighted sampling approach assigns recently interacting neighbors higher probabilities following an exponential distribution. And the recent sampling approach simply selects the top k recent temporal neighbors for facial aggregation. The figure suggests that the most recent temporal neighbors play a more crucial role in learning high-quality temporal embeddings, since the recent sampling approach clearly outperforms other neighbor samplers in model performance. Moreover, the figure on the right shows the weights of the top 10 recent temporal neighbors learned by TGN on 6 real-world dynamic graphs. So notably, the weights approximately follow exponential distribution irrespective of the input features. Inspired by the observations, we propose temporal personalized PageRank, or TPPR, a novel parameterized metric for estimating the influence score of temporal nodes on dynamic graphs. In TPPR, the temporal random walk terminates at the current position with probability alpha. We move to a temporal neighbor with probability 1 minus alpha. Besides, TPPR is equipped with an exponential decay factor assigned the k's recent temporal neighbor transition probability proportional to the beta to the power of k. Our intuition is that recent interaction captures the latest trend and thus convey more information in the diffusion process on dynamic graphs. Finally, we present a new system named Zebra that improves TGN with TPPR. The given target temporal nodes, we first get its top k influential neighbor nodes by solving the top k TPPR query. Then we compute the temporal embedding through simple one-layer neighborhood aggregation. So compared to vanilla TGN, our Zebra framework can be exponentially faster. The configuration of TPPR used in Zebra is important since the quality of generated temporal embeddings highly depends on the choice of TPPR parameters alpha and beta. The single TPPR, if not well parameterized, may fail to sufficiently capture the diffusion process on evolving graphs, thus degrading the model performance. To address the above limitations and for practitioners from laborious parameter tuning, we propose to build robust TGN through uniting the express power of diversified TPPR metrics. So as shown in this figure, the TPPR metrics parameterized by different alpha and beta parameters are endowed with distinct receptive fields. In general, TPPR configured by large alpha and beta values can widen the receptive field of Zebra, while small alpha and beta values deepen the receptive field. Next, I will introduce how we solve the top k TPPR query problem. The core technical challenge of Zebra is to answer top k TPPR queries efficiently. Otherwise, the computational costs saved from avoiding recursive temporal neighborhood aggregation could be overconsumed by the query algorithm itself. Although many advanced techniques have been developed for PPR or personalized PageRank query processing, they cannot be adapted to efficiently answer top k TPPR query due to the highly imbalanced weight distribution. A straightforward solution to the top k TPPR query is power iteration, which recursively traverses the graph and then selects the top k temporal nodes. However, this approach is computationally prohibitive as its costs increase with number of temporal edges in the dynamic graph. So we developed an efficient single-scan top k TPPR algorithm named Santa that creatively prunes a significant temporal nodes. So for each node in the dynamic graph, we maintain an approximately top k TPPR dictionary that records the top k influential temporal nodes and the corresponding estimated TPPR values. So given new interaction, Santa updates top k TPPR dictionary for node weight I by merging two parts, the corresponding two parts in a streaming fashion. Then we keep the top K influential neighbor nodes in the dictionary. We have developed approximation guarantee for our Santa algorithm. And our series shows that the active error bound, the active error bound here shows that the active errors of Santa are negligible when the temporal random probabilities are highly skewed, or large K is adopted. Besides, the relative error bound indicates that the errors of estimate TPPR values can be marginal for the most influential temporal nodes. Next, I will introduce the experimental results. We compare our zebra framework with 5 state-of-the-art baselines and 6 dynamic graphs in experiments. As for effectiveness, we compare models' average precision on the test set. More specifically, we consider 2 types of tasks: transductive learning and inductive learning. The transductive learning task examines model performance and nodes that have been observed during model training. In contrast, the inductive task tests the learning ability of models on unseen nodes. As for efficiency, we evaluate the per epoch training time and the total training time till convergence. The table shows the experiments on large dynamic graphs. So Zebra is 1 to 2 orders of magnitude faster than the compared baseline in total and per epoch training time. Zebra is computationally simple as it avoids the tedious process of temporal massive passing by efficiently solving the top K TPPR query. Besides, Zebra can even outperform the best baseline in prediction accuracy. So Zebra can also significantly reduce memory consumption of TGNs. Zebra reduces the computational cost of TGNs and thus saves the GPU memory required to perform the corresponding computations. For instance, the peak GPU memory consumption of the baseline TGN is 3 gigabytes more than that of Zebra on the Wikitalk dataset. Overall, the experimental results show that Zebra is memory efficient and scalable to large dynamic graph. And the table here investigates the impact of ensemble size on Zebra's performance. Clearly, an ensemble of 2 TPPR metrics outperform a single TPPR metric in average precision. The observation here is in line with our expectations, since an ensemble of 2 diversified TPPR metrics can enlarge the receptive field of Zebra and thus improving models' generalization ability. Besides, increasing the ensemble size may not improve Zebra's performance. Increasing the ensemble size could introduce harmful noises and irrelevant temporal nodes. The noises lead to the oversmoothing issue and prevent the model from focusing on the most informative temporal nodes. In summary, in this paper, we build a theoretical connection between temporal massive passing in TGN and the temporal random walk on dynamic graphs, within proposed temporal personalized PageRank, a novel parameterized metric for estimating the influence score of nodes on dynamic graphs, and develop an efficient single-scan algorithm to answer the top K TPPR queries with approximation guarantees. Finally, we present Zebra, a scalable framework for accelerating the training and the inference of TGNs by solving the top K TPPR queries. Thank you for listening.